firstly, you can see that this is just a combination of two concepts. First is linear equations, and then you now have a system of it. Okay, so first of all, we are then going to begin from what a linear equation is. Okay, so what then is a linear equation? So by definition, we are going to begin with the definition of a linear equation. Okay, so we say that a linear equation is an equation that is of the form a1 x1 plus a2 x2 down to an xn being equal to b, maybe we can call it bn if we want. Okay, so or you can just say equal to b. We can just say equal to b. So this is the general form of a linear equation. And what does that mean? So in simple terms, we can say it's an equation where the variables have a power of 1. So every single variable present in a linear equation is always to the power of 1. So it could be more than one variable, like we have here. X1 is a variable, x2 is another variable, and up to xn. So that is to say that the variables present in the equation can be up to n, depending on what you want. It could be a 2-variable equation, a 3-variable equation, or even a 1-variable linear equation. For instance, I can have something like 2x is equal to 5. This is a very beautiful linear equation because here I have one variable and the power of that variable is what? 1. Because of course by indices we are told that the power of any variable in this form is the same as 1. Alright, so and you can have examples of two variables, maybe 2x, instead of just only 2x, we can have plus, let's say 5y to be equal to maybe 0. Alright, so this now is a linear equation in 2 variables. We can have linear equations in 3 variables, 4 variables, and up to n variables. Alright, and so where your a's are scalars. You know, whenever we talk about scalars, remember under vectors we saw that whenever we talk about scalars, we are just talking about your normal constants. Okay, so like here you have 2. In this case, now your A's and B's, your AI's, that's how we can write it, AI's. Okay, so of course this is A1, A2 up to AN, or you can say AI's, alright? So, and your B are your normal scalars or constants, right? So that is why I also have 0 here, because 0 is also a constant. Okay, so we can have other examples. Now then, of course, in a way to make this more beautiful, instead of using different variables, we choose to use a single variable with subscript. So instead of writing 2x plus 5y, I can actually just write 2x1 plus 5x2 equal to 0. So now here I am using the same variable. I am only distinguishing the two with the subscript. So the subscript 1 here makes the x1 completely different from your what? X2. Okay, so this is what a linear equation is. An equation of this form. This is the general form. And in literal terms, you can say an equation where you have variables with powers as what? 1. And then some constants, you know, in, of course, constants as coefficients of the variables and a constant on the other side of the equation. Because for it to be an equation, there must be an equality sign. Alright, so this is where we are starting from. So now what then is a system of equation? So a system of equation is now a combination of two or more equations. When you have a combination of two or more equations in one, what then you have is a system. So for example, I can have something like, let's say x1 plus maybe 2x2 is equal to say 5, and then I can also have, let's say 2x1 minus, let's say 4x2 is equal to 0. So this is an equation which we can call equation 1, and then the second one is another equation 2. And so when you have the two of them together, what you have now is a system. It's containing or comprising of more than one equation. So in systems of equations, you now begin to talk about the number of variables and the number of equations. In a normal linear equation, you're only referring to the number of equations or number of variables. That's why I was talking about a linear equation of one variable, a two variable linear equation, three variable linear equation. But when we now have a system, we will now be talking about the number of variables and the number of equations present. Of course, as we continue, we are going to give you a representation for all of those. Of course, the representation for number of equations is your number of variables is n, while number of equations is r. We will still get to all of this. Okay, so here you can say that this system is a system of two equations in two variables. This is a system of two equations in two variables. So if I add something else here, let's say minus x1 maybe plus 3x2 is equal to, let's say, 4. So here now I have a system of three equations in two variables. It is still having only two variables. However, there are now three equations in this system. Now, remember that the essence of every equation is that the equation should be solved. If you give me an equation, the expectation is that the equation should have a solution. Or in any case, there are equations that may be without solutions. Of course, as we progress, we'll see all of those. Such equations or systems are called inconsistent equations or inconsistent systems. Alright? Systems of equations, you can actually define them using the general form. So the definition for or the general form for systems of linear equations is given this way. Now you can give it this way, say a11 x1 plus a12 x2. I'm going to explain all this nomenclature, and then down up to a1n xn to be equal to b1, and then the next one a21 x1. Now let me give an explanation to all of this. Of course, like I said, these are just representations or nomenclatures. Okay, so your a's represent coefficients, just as you have here. What it means is, in this equation, remember, your n is only telling you the number of variables present. So the n in this equation is actually 2, because there are only the number of variables present. So the n here is equal to 2 because there are 2 variables present, while the n here is also 2 because, in this case it's now 3 because there are 3 equations. So the first digit is telling us the position in terms of column. It's telling us the number of the equation. So this time means the A11. This one means equation 1 and variable 1. So this A is the A that is in equation 1 and together with variable 1. So the second one is talking about the variable. Like here you can see the 2 here is together the same as variable 2. And that is the same for the last one. So now you can see that all the A's in the first equation, the first subscript is all 1, all through. So that's talking about equation 1. And even the B has 1 also there. Now look at equation 2. In the 2 here now is talking about the position of the equation. So you can see the first subscript here is 2, all through. Alright, while the second one here is talking about the variable. So this is the A of equation 2, variable 1, A of equation 2, variable 2, A of equation 2, variable n. And you can see all the variables there. Down to here. So this is A of equation n, variable 1, A of equation m, variable 2. And you will always see your B having the same subscript as the first subscript of your A. because it's showing that all of them are in the same equation, but the variables can differ. Of course, the variable 1 will carry 1 here, variable 2 will carry 2 here, and so on. Alright, so this is the general representation or general form of every system of equation. So what it means is that if I give you this equation now and ask you to get for me the A12, the A12 means the A of equation 1 variable 2, and that is my what? My 2. So that means here now A11 is equal to what? 1. That's the coefficient of x1. While my A12 is the coefficient of the second variable, and that is equal to what? 2. So if I say give me A32, that means I'm looking for the coefficient of the x variable in equation 2 variable 2. So I'm looking for, equation 3 variable 2. So I count 1, 2, 3. This is my equation 3. And what is the variable 2? The variable 2 is x2. So I look for the coefficient there, and that is equal to what? 3. And that is that. So here you can say our B1 is 5, our B2 is 0, and our B3 is equal to 4. So all of these are just nomenclatures and representation. So what do you think this one is going to be? What is minus 4 going to be in terms of nomenclature? So of course that's equation 2. So that will be A2, and that is variable 2. That will be A22. That will be equal to minus 4. So this one now is going to be A21, and this is going to be A31, and so on and so forth. Okay, so now beyond giving a general representation for systems of equations, it is also important that we look at types of systems. So that is where we'll probably end for this video. And in our next one, we'll now begin to talk about solutions of systems of equations, how to solve them using what we call elimination approach. That's Gaussian elimination, to transform every system of equation to what we call the echelon form or the triangular form. Okay, so we have basically two types that I'm going to mention here that is important for us in this particular course. And one is what we call the homogeneous system. And then we also have what we call just the opposite of it, the non-homogeneous. So a linear equation can be homogeneous or non-homogeneous. So by definition, what does it mean for a system of equation to be homogeneous? Very simple. Now look at it here. If you have, let me even use the general representation. If I have any system of equation such that all my bi's, so I'm defining homogeneous now, if all the bi's are equal to 0. In other words, what this thing means is that if my B1 is equal to B2 equal to dot dot up to Bn, if everything is equal to 0, then the system you have is a homogeneous system. You will see how beautiful this is when we begin to interact with systems of equations, other solutions, and other things that we are going to see here, such as the concepts of linear dependence and linear independence. We are going to see how beautiful the concept of homogeneous system is going to be. Alright, so an example is something like this. From what I just explained now, you could see that the system I gave here is actually non-homogeneous because all the b's are not all what? Zeros. It's only the b2 that's equal to 0. So assuming we decide to make everything here to be all zeros, then the system you have becomes what? A homogeneous system. And if all your b's are not all zeros, even if it is one of them that is not 0, what you have is what? A non-homogeneous system of linear equations. And you can give yourself many examples of that. For example, we can have something like x1 plus maybe 2x2 again. So what kind of a system is this? First of all, is this a system of linear equation? You can tell your answer is yes. How many equations and how many variables? Okay, you can see the first equation has only 2 variables. and the second has 3. The third has 2. So what can we say about the number of variables in the equation? First of all, we know that the number of equations now is 3. That means our R is 3 and our N, the number of equations, the number of variables will be what? It will also be 3. Now, why is it so? You assume the number of variables to be the highest that is present. In this case, the first equation has only 2 variables, the second has only 2. But the third has only 2. But the second has 3. So the one that has the highest number of variables. And not just that, you look at the subscript. So the subscript should tell you the number of variables present. Because now, what's the highest subscript here? The highest subscript is what? 3. So that means there are 3 variables present. The only thing is that the third variable here was probably multiplied by 0. So we can write something like 0x3 to be equal to 0. So of course, anything multiplied by 0 will also disappear. So it means that the coefficient of this x3 here is what? 0. And the same thing is applicable here. You can see that the one missing here is your x2. So the implication is that my x2 was also multiplied by 0. And then x3 all equal to 0. So you can see all the variables are actually present. The only thing is that their coefficients were actually 0. Alright, so to know the number of variables in an equation, you look at the subscript. The highest subscript tells you, it may not necessarily be the one that has the highest number of variables, because it's possible to have something of this nature. Look at this. Let me use that same example. 5x1 plus x2 equal to 0, and the second one is minus 2x1 plus x2 plus x3 equal to 0. And let's say the third one is 3x1, let's say minus 2x4 is equal to, let's say, 0. Or let me even put a number here, maybe 1. So how many equations are here? There are still 3 equations. And how many variables do we have now? There are 4 variables, because there is x4 present. So that means you have x1, x2, x3, and x4. So the one showing us the presence of x4 is actually having only 2 variables. But this one has 3 variables. It only stopped at x3. So you don't actually use the one with the highest number of variables. You just look at the subscript. So the highest subscript tells you the number of variables present. So what it means here is that x3 and x4 are missing. So their coefficients are 0. Here, only x4 is missing, so the coefficient is what? The coefficient of x4 is 0. Here, x2 and x3 are missing, so their coefficients are 0. Now, let's get back to the what I was trying to show us here. So you can see that this is a homogeneous system. All our constants on the right-hand side are all zeros. So it's a beautiful homogeneous system. Whereas this one I have here is a non-homogeneous. Even though that 2 of the equations are having the constant to be 0, that doesn't matter. So far as one of the constants is not a 0, what you have is a non-homogeneous. So in a summary, what we did was to introduce the topic systems of linear equations, and we started by defining a linear equation and showing us a general form that is of this form: a1x1 plus a2x2 dot up to anxn to be equal to a constant b. So if this happens, you have a linear equation. And then we now went further to look at systems, and we said that a system is now a combination of 2 or more linear equations. It could be 2 equations in one, 3 in one, 4 in one, and so on. And here we said that a linear equation could be in 2 variables, in 1 variable, in 3 variables, as the case may be. Now, for the system, we said here you will now be looking at the number of equations and the number of variables. So you can say a system is a system of, say, 2 equations in 4 variables, or a system of 3 equations, like this one now is a system of 3 equations in 4 variables. This one is a system of 3 equations in 3 variables, and so on and so forth. And so we're also able to see the two major types of a system, and we saw the homogeneous when all the constants on the right hand side are all zeros, and we saw the non-homogeneous when there is at least one that is not a zero. Then we say we have a non-homogeneous. So like I said, in our next class we'll be looking at how to solve systems of linear equations. Please do subscribe to our YouTube channel, and we'll see you in our next video. Bye.